In these examples, we can apply these new exponent properties, or we can do these ones as radical problems. So we can do them either way. So I'm going to do the first one here as a radical problem. Really what I'm going to do is, well, I know that if I do a power 5 on a fifth root, I undo the root. So I'm going to rearrange this as x to the power, the fifth root, to the power 5. That's going to undo the power, and I have squared. So if I power 5 and square it, that's the same as power 10, so I'll highlight that. This power 10 is equivalent to this and this. And this is going to undo, so I'm going to end up with x, and I'm just going to be left with 2. Here, same thing, I can do the fourth root, and I'm going to do x squared to the power 4. So I can see that these two powers then cancel. Okay, these are the fourth root, fourth power, they undo each other. And so I'm going to be left with times, again remember that this is all implied multiplication between here, times x squared, and that gives us x to the power of 4. So there are lots of different ways to do this. In this case here, when we multiply these are really quite difficult to multiply because if the indexes aren't the same, we really shouldn't multiply them. But what we've been able to do is get rid of the roots. So we're just talking about x's, and we can then go ahead and multiply them. As exponent rules, we could have done this slightly differently. I could have written this as power 10 root 5 times x to the power 8 root 4. This becomes x squared, this becomes x squared, and again we get the exact same answer of x to the power 4. So one is using this property of power and root undo each other. Okay, the other one is using this exponential property that the power is the numerator of the exponent and the root is the denominator of the exponent, and that ratio can be simplified. Here I'm going to use exponent properties. So 1/2 to the power 3 is going to give me 3 over 2. So power 3 root 2, there's my square root. Here I have power 5 root 2. Again, I can just put those together because the power and the roots have no precedence over each other, so they can go together and they can be expressed in one fraction. My exponent rules state that if I multiply with the same base, I can add the exponents. Here I have an exponent with a common denominator. This becomes 8 over 2. That simplifies to a to the power 4. We have to be really careful once we have numbers involved here, because we have to be careful of what is the base of the exponent and what is not the base of the exponent. So here, the base of this power 1/5 is x, but the 2 is not part of this power 1/5. However, because of the brackets here, the 2 is a base of 3. So this power 3 is going to be applied to the 2 and the x. Here the power is applied only to the x, etc. So let's first of all do our power here. And this is times, and remember power and times are compatible. If it was a plus there, we'd be in big trouble. Power and plus and minus are not compatible. So because there's a times in there, we can apply that. We can do power 3 root 5 times power 2 squared is power 4 root 5 times power 3 root 5. So I can work out this 2 to the power 3 is 8 times, since these are all the same bases of x, I can put those x's together as 3/5 plus 4/5 plus 3/5. Okay, that works out to be 8 to the times x to the power 10/5. Okay, which is really the same as the ratio of power 10 root 5 reduces to a ratio of 2 to 1. Okay, so here we can do this different ways. We can say that, well, a square root to the power 4, well, square root times square root times square root times square root gives us a power 2. We can do that. We can rewrite it as an exponent. Okay, and we can see that the ratio of the root to the power is going to give us a 2 to 1 ratio. So same thing here. We can group them into powers and roots that will undo each other as well. That's another way to do it. So we'll do it two ways. So here I'm just going to use the exponent rules. I'm just going to convert this to exponent. So remember that my base, the root is applied to the a cubed. The power 4 is applied to the a cubed. So power 4 root 2. Okay. That extra a cubed in there sometimes is a little hard to determine. That root is this root here. Okay. In the next one, well, this is easier because there's only one power involved. Power 15 root 5. That's going to reduce to a cubed. This becomes a to the power 4. So this is a squared, a cubed. So I'm going to rewrite this. A cubed squared times a cubed over a to the power 4. That can be simplified. So that's 6 a's, 9 a's on top, 4 a's on divide. So it becomes a to the power 6 times a cubed over a4. A to the power 9 over a to the power 4. And this simplifies to a to the power 5. Okay, so that's one way we can do it. We can just simply do it as an exponential problem. The other way we can do this is I can do this. I can split my power 4 into squared and squared. Okay, well that's going to undo that square root. Here I'm going to end up with root 5, or sorry, fifth root to the power 5, fifth root to the power 5, okay, and the power 15, to make the power 15, I need to have fifth root power 5 again. Okay, so maybe I'll just do this in blue here, group that in blue. Okay, so that power, this a to the root 5, the fifth root of power 15, I can just keep my root and show my power 15 as power 5, power 5, power 5. Okay, so that power, what I've done then, and I'm just going to make sure I don't forget my a to the power 4. This one's a little bit harder to do, I think, so I think maybe exponents might be easier, but what we're doing then is we're going to just say that this power and this root undo each other. This power and this root undo each other. So I'm just going to highlight that. So this root and power undo each other. This root and power, root and power undo each other. Okay, so what do I have left? I'm going to be left with a cubed times a cubed. There's my a to the power 6 that I ended up with here, times fifth power, fifth root, fifth power, fifth root, fifth power. That means I have just the a left over from that there. And finally, a to the power 4 on bottom. So if I count this all up, 6, 7, 8, 9. There's my a to the power 9 on top. A to the power 4. 4 times cancels with 4 divides. So I'm left with a to the power 5. So again, notice that these are different approaches to it. One is an exponential approach, but that ratio of powers shows up like this. I can put it into groups of 5. Okay, and that grouping is the same as a ratio and allows us to simplify our power and root fractions.